Tonight, we turn our attention to a neighboring world, Mars. Today, it appears dry and cold, but it was not always this way. Its surface is carved by river valleys wider than anything on Earth, shaped by flowing water that returned again and again. There was a time when Mars held warmth, when water moved freely across its surface, when the planet had the conditions life needs to persist. On paper, Mars should have kept that world alive longer than it did. It formed alongside Earth, warm within, active, and protected. The oldest rocks on its surface preserve evidence of a magnetic shield, once strong enough to stand between the planet and the Sun. But what happened? Why did Mars lose its protection while Earth did not? What caused a planet with rivers and lakes to cross a threshold it could never return from? Tonight, we follow the traces left behind in stone and sky, listening to what a planet reveals long after its voice is gone. But before we begin, if you're already enjoying this moment of quiet wonder, it would mean a lot if you gave this video a gentle like or subscribed for more sleepy science journeys like this. And if you don't mind, tell me in the comments where in the world you're watching from tonight and what time it is there. It's always a joy to see how far across our planet these sleepy science videos drift. Now take a deep breath, let your body relax, and together let's drift back to the time Mars was still alive. Mars did not begin as a lesser world. It emerged in the same early turbulence that shaped Earth, condensed from the same swirling disk of dust and gas, forged by the same collisions and heat. In its earliest moments, the difference between the two planets was not obvious. Both carried the memory of fire beneath their surfaces. Both gathered atmospheres from their surroundings. Both cooled just enough to let solid ground form. In that young solar system, nothing marked Mars as temporary. Beneath its surface, early Mars was active and restless. Heat still moved through its interior, shifting rock, driving circulation, keeping the planet alive from the inside outward. That internal energy mattered more than appearance. It powered processes that could shape a world across millions of years. It allowed the crust to breathe, to exchange gases, to release warmth upward instead of trapping it below. For a time, Mars had a working engine, quiet but persistent. Above that surface, the planet held an atmosphere thick enough to matter. Air pressed downward with more strength than it does today, enough to stabilize liquid water instead of forcing it to vanish. Heat lingered rather than escaping immediately into space. Clouds could form, precipitation could fall, and the surface could remain wet long enough for change to accumulate slowly instead of flashing away. Mars was not merely damp for brief moments, it stayed that way. Water followed naturally from these conditions, not just as frost or fleeting melt, but as flowing systems that returned season after season. Valleys did not appear by accident. Lakes did not last by coincidence. These required time, repetition, and patience from the planet itself. Water cycled, interacted with stone, altered minerals, and left chemical signatures that only form when liquid remains present for long stretches. Mars had stability, and stability is the quiet requirement behind every lasting environment. Taken together, these pieces formed a foundation that should have endured. A warm interior, an atmosphere able to hold heat, water capable of returning instead of disappearing, and geological activity able to refresh the surface rather than let it stagnate. By comparison, Earth retained these qualities for far longer, but early Mars possessed enough of them to remain viable well beyond its youth. On paper, nothing demanded an early end, yet planetary survival is not decided by possession alone. It depends on maintenance. Energy must continue to circulate. Air must be replaced as it is lost. Protection must remain in place long enough for recovery to occur. Mars carried what it needed at first, but it did not carry enough margin. Its systems were thinner, smaller, more easily slowed. The balance it held was real, but fragile. Failure did not arrive as an event that could be witnessed. There was no sudden absence, no single transformation that marked the shift from capable to doomed. Instead, a support weakened, a process slowed. Something that once worked quietly in the background began to falter without announcement. The planet did not know it was losing anything essential until replacement was no longer possible. This is the only foundation that matters. Mars began with the same promise, built from the same materials, animated by the same early energy as Earth. It had warmth where it counted, air that stayed, water that returned, and time enough for complexity to grow. Its fate was not sealed at birth. It unfolded later, step by step, as one crucial function after another slipped out of alignment and never fully recovered. Long before rivers carved valleys and lakes settled into basins, something unseen wrapped itself around Mars. It had no color and no surface, yet it shaped the planet's future as surely as rock or water. Deep beneath the ground, motion within the planet's core generated a field that extended outward into space. It moved silently, bending invisible forces around the world, standing between Mars and the constant stream of energy pouring from the sun. This magnetic field did not create life or climate on its own, but it made both possible. It acted as a shield, guiding charged particles away from the upper atmosphere and preventing them from striking it directly. With that protection in place, air could remain aloft instead of being slowly peeled away. Heat could linger, chemistry could proceed undisturbed, and the planet's surface could exist without constant erosion from space itself. The field allowed Mars to keep what it had already built. The presence of this shield is no longer inferred from theory alone. Its memory is preserved in stone. Ancient volcanic rocks across the Martian surface hold patterns that only form when molten minerals cool within a magnetic field. Each grain aligned itself with forces that no longer exist, locking in a directional record of a planetary defense that once surrounded the world. These rocks are quiet witnesses, confirming that Mars was once protected in the same fundamental way Earth still is today. For a time, that protection held. The atmosphere stayed thick enough to matter, and the upper layers were not freely exposed to the sun. Solar radiation flowed around the planet rather than through it. This allowed slower processes to shape the surface, ones driven by water, chemistry, and time instead of by relentless particle bombardment. The field did not stop loss entirely, but it slowed it to a pace the planet could tolerate. Then the shield began to weaken. The change did not announce itself in the sky or on the ground. As the interior of Mars cooled, motion within its core gradually slowed. The engine that sustained the magnetic field lost strength. The field did not shatter or flicker out in an instant. It thinned, contracted, and finally faded beyond usefulness. When it was gone, the planet stood exposed in a way it never had before. Without that protection, the upper atmosphere became the first to suffer. The solar wind, a constant flow of charged particles from the sun, could now strike directly. Each impact carried energy, and each interaction stripped away a few more atoms of gas. The loss was subtle on any given day, but relentless across geological time. The atmosphere was no longer held in place by both gravity and shielding. Gravity alone was not enough. This single failure altered the direction of everything that followed. Air could leave faster than it could be replaced. Heat slipped away more easily. Water became harder to stabilize, then harder to retain at all. The planet did not change all at once, but its balance shifted permanently. With the shield gone, Mars lost its ability to protect what it already had. From that moment onward, the world was no longer defending itself against space, it was enduring it. Light from the sun always reached Mars, but there came a time when it reached too far, not in brightness or warmth, but in contact. High above the surface, where the atmosphere thinned into space, sunlight arrived carrying more than heat. It carried charged particles moving fast enough to matter. On worlds with protection, these particles are guided aside, curved away before they can touch the fragile upper layers of air. On Mars, that guidance had faded. Once exposed, the sky itself became the first place where change took hold. The upper atmosphere began to interact directly with the solar wind, a steady flow of energetic particles streaming outward from the sun. Each collision was small, almost insignificant on its own. An atom struck here, a molecule nudged there, yet the interactions accumulated. Over time, momentum transferred from the solar wind to atmospheric particles, lifting them higher, accelerating them, and sometimes giving them just enough energy to escape entirely. This was not erosion as the surface experiences it. There were no marks left behind, no visible scars. The loss happened above sight, in a region where gas grows thin and boundaries blur. Charged particles stripped electrons from atoms, turning neutral gas into ions that no longer behaved the same way. Once charged, these particles were easily caught by electromagnetic forces carried with the solar wind itself. Instead of falling back toward the planet, they were pulled outward and carried away. The atmosphere did not collapse, it loosened. Each day, a tiny fraction of air drifted upward and failed to return. Gravity still held most of it in place, but gravity works slowly at such heights, and the solar wind never paused. The balance that once favored retention tipped subtly toward loss. There was no clear moment when the change could be noticed from below. The surface remained solid, the sky still present, but the connection between them was weakening. As more particles escaped, pressure at the top of the atmosphere decreased. That change propagated downward, layer by layer. With less pressure above, gases expanded slightly, thinning the upper regions further and making them even easier to strip away. The process fed itself quietly. Nothing dramatic accelerated it, yet nothing stopped it either. Mars had entered a phase where loss became routine. The sun did not need to grow stronger for this to happen. Its steady output was enough. Over millions of years, even a modest rate of escape became decisive. What mattered was duration. The exposure was permanent, and time was abundant. The atmosphere slowly bled outward, not in a rush, but in a continuous whisper. Each particle that left carried with it a trace of warmth, a fragment of pressure, a small piece of the climate Mars once maintained. As the air thinned, its ability to shield the surface weakened as well. Radiation penetrated deeper, chemistry shifted, and the remaining atmosphere became more vulnerable to further interaction. The system no longer repaired itself. Loss did not trigger replacement at the same rate. Volcanic contributions, once able to balance escape, no longer kept pace. The sky was no longer sealed. This was the moment Mars became open to space in a way it never had before. Not suddenly, not catastrophically, but completely. The planet remained intact, its surface largely unchanged in outline, yet the connection that had held its air close was gone. From then on, Mars existed beneath a sky that could not fully stay. The atmosphere continued to thin, particle by particle, drifting away into the silent flow surrounding the sun. Air does not remain around a planet by chance. Even when gravity is strong, loss is always present, always working quietly at the edges. What allows an atmosphere to endure is not the absence of escape, but the presence of renewal. Worlds that keep their skies do so by feeding them continuously, returning gases to the air as others drift away. The exchange is subtle, steady, and easily overlooked when it works well. On active planets, the interior plays a central role in this process. Heat rising from deep within keeps rock moving and pressure building. Gases trapped underground are released through fractures, vents, and eruptions, seeping upward over long spans of time. Volcanoes are not only engines of destruction, they are conduits. They breathe material into the sky, restoring what solar radiation and particle escape slowly remove. This balance allows an atmosphere to remain thick even while it leaks. Early Mars participated in this exchange. Its interior still carried enough warmth to drive volcanic activity across wide regions. Lava reached the surface, gases were released, and the atmosphere could recover from losses occurring high above. The system did not require intensity, it required persistence. As long as input roughly matched output, the sky remained stable enough to support the surface below. That persistence did not last. Mars, smaller than Earth, held less internal heat to begin with. Over time, that heat bled away into space. The interior cooled, and with cooling came stiffness. Rock became less willing to move, pressure less eager to build, pathways less likely to open. Volcanic regions that once renewed the atmosphere grew quieter. Eruptions became less frequent, then rare. Eventually, many stopped altogether. The change did not announce itself on the surface in obvious ways. There was no sudden stillness. Instead, intervals between activity lengthened. Gases entered the atmosphere more slowly, then sporadically. The loss continuing above did not pause to match this decline. Solar stripping, chemical escape, and gradual thinning carried on with quiet consistency. The sky was losing material at a steady pace, while the planet beneath it was losing its ability to respond. This imbalance altered the nature of Mars's atmosphere. What had once been a circulating system became a dwindling reserve. Each particle that escaped was less likely to be replaced. Pressure decreased incrementally, then meaningfully. Lower pressure allowed gases to expand upward, making them more vulnerable to loss. The cycle fed itself gently, without violence or spectacle. Volcanic silence carried another consequence. With fewer eruptions, fewer greenhouse gases entered the sky. Heat retention weakened, surface temperatures fell, and chemical reactions slowed. Cooling reinforced the stillness within the planet, further suppressing internal motion. The engine that might have recovered the system lacked the energy to restart. What was lost was not just gas, but resilience. Mars reached a point where loss no longer needed acceleration. It only needed time. The atmosphere thinned gradually, each stage making the next easier to reach. Water responded to this shift, but the process began higher, in the air itself. The sky became too fragile to sustain the conditions it once supported. Not because escape increased suddenly, but because renewal faded away. This was how the balance tipped. Quietly, without a single defining moment, Mars transitioned from a world that could repair itself to one that could not. Air continued to leave, one particle after another, while the planet beneath remained largely still. The exchange that sustains planetary skies had slowed beyond recovery. From that point forward, the atmosphere was living on borrowed time, thinning steadily as the deep interior grew ever more silent. Water behaves differently when the weight of the sky above it begins to lighten. On Mars, this change arrived quietly, almost imperceptibly at first. The surface still held basins shaped to contain lakes, channels shaped to guide rivers, and ground altered by long contact with liquid water. Yet the invisible force pressing down from above was weakening. As atmospheric pressure fell, the rules governing stability shifted. Liquid water requires balance. Temperature matters, but pressure is just as critical. When pressure drops below a certain threshold, water no longer lingers in liquid form. It begins to boil at lower temperatures or transition directly between ice and vapor. On Mars, as air thinned, water found itself increasingly out of place. What had once been comfortable conditions slowly edged toward instability. Lakes were the first to show this change. They did not vanish all at once. Instead, their margins retreated. Shorelines pulled inward season by season, leaving behind rings of sediment and mineral deposits that traced former extents. Evaporation increased, not because heat surged, but because the atmosphere no longer pushed back. Water molecules escaped more easily from the surface, rising into thin air, where they were less likely to return. Each year, more was lost than replaced. Rivers responded more subtly. Flow became intermittent. Channels that once filled reliably during wet cycles began to run dry between seasons. Water that reached the surface lingered for shorter periods, soaking into ground or lifting away into vapor before it could travel far. The familiar rhythm of return weakened. Streams no longer re-established themselves with the same consistency. What had been a repeating system grew hesitant. As pressure continued to fall, freezing gained ground. Lower atmospheric insulation allowed temperatures to swing more sharply. Nights grew colder, winters harsher. Water that might once have remained liquid froze more readily, locking itself into ice before it could circulate. Frozen water was not gone, but it was immobilized, no longer participating fully in surface processes. The landscape retained its shape, but the motion that carved it slowed. This period marked a shift in character rather than appearance. Mars had not yet become the frozen world it would later settle into. Liquid water still appeared, but it was unreliable. It arrived briefly, behaved unpredictably, and departed without sustaining long cycles. The planet entered a state where water could no longer plan on remaining where it fell. Stability gave way to chance. These changes fed back into the atmosphere itself. With less exposed water, fewer gases entered the air through evaporation and chemical exchange. The sky grew drier, as well as thinner. Clouds became rarer, precipitation less frequent. Without consistent surface water to buffer temperature and chemistry, variations intensified. Mars began to oscillate between brief moments of activity and long stretches of dormancy. Nothing in this transition was abrupt. There was no final lake, no last flowing river that could be identified as an ending. Instead, each feature faded at its own pace, responding locally to a global shift. Some basins held water longer than others. Some channels carried flow after their neighbors had already fallen silent. The planet did not cross a single line. It drifted across many. This instability defined a long Middle Age for Mars. Not fully alive with surface water, not yet entirely locked in ice. The air was still present, the cold not absolute, the ground still capable of change. Yet the system no longer supported itself. Water followed pressure downward, retreating from the surface as the sky above it grew too light to hold it there. Mars continued on, altered but intact, moving deeper into a state where liquid water became an exception rather than a foundation. The last long-lived lakes did not announce themselves as endings. They appeared as continuations of something already fading, occupying basins that had held water many times before. These bodies of water were quieter than their predecessors, more restrained in size and behavior. They filled slowly, lingered cautiously, and changed shape with a sensitivity that earlier lakes had not required. Their persistence was real, but it carried a different quality, one shaped by uncertainty. Geology preserves their presence with careful honesty. Layered sediments settle in patterns that require time without interruption. Fine particles drifted downward through still water, arranging themselves into thin bands that could not form in brief floods or sudden melts. Along the margins, minerals concentrated where water repeatedly pulled back, then returned, marking shorelines that migrated inward over long periods. These signatures record stability but also retreat. Evaporation left its mark with equal clarity. As water remained exposed beneath a thinning sky, dissolved salts and minerals were left behind. They crystallized at the edges and across shallow flats, forming deposits that speak of repeated loss rather than continuous renewal. In other places, textures reveal cycles of freezing and thawing, ice forming at the surface or along the bottom, then giving way briefly before returning. Water still occupied these basins, but it behaved cautiously, constrained by conditions that no longer fully supported it. These final lakes did not depend on constant inflow from distant sources. Many were fed by local groundwater, rising slowly from beneath the surface, where ice melted or pressure shifted just enough to allow release. This hidden supply prolonged their existence, allowing liquid water to persist even as surface conditions grew harsher. The lakes remained, but they did so by retreating inward, relying on what lingered below rather than what arrived from above. Reliability was the first thing lost. Water still appeared, but it no longer followed predictable rhythms. Levels fluctuated with subtle changes in temperature and pressure. Some years left distinct layers, others left almost nothing. The environment could no longer promise continuity. Each return of liquid water was conditional, dependent on circumstances that grew narrower with time. The lakes endured, but always on the edge of disappearance. As these changes unfolded, the surrounding surface responded. Without constant water to soften it, ground began to stiffen. Sediments that had once been reworked by flowing liquid settled into place and remained there. Chemical reactions slowed. Soil structures locked together, and erosion shifted from water-driven processes to slower, drier forms. The landscape did not freeze instantly, but it began to resist change. The hardening of the surface altered how future water behaved. When liquid appeared, it was less able to infiltrate deeply or reshape the ground. It pooled, evaporated, or froze where it stood. Channels no longer evolved significantly. The planet's exterior took on a more static quality, preserving older features rather than creating new ones. Mars was beginning to keep records instead of rewriting them. These last, long-lived lakes represent a boundary rather than a finale. They existed long enough to leave unmistakable traces, yet not long enough to sustain a broader system. Their presence confirms that Mars retained liquid water well into its decline, but only in isolated pockets, under conditions that no longer favored expansion. They were remnants of a world transitioning away from surface activity. When these lakes finally faded, they did so without spectacle. Water retreated underground, locked itself into ice, or escaped into the thin air above. What remained was a surface that remembered their outlines but no longer responded to them. Mars continued onward, carrying the quiet record of these final waters, etched into rock that had begun, at last, to settle into permanence. Size determines how long a planet can hold on to its warmth. Mars was built smaller from the beginning, not flawed, but limited in what it could store. Heat generated during formation escaped more easily through a thinner body, traveling a shorter distance from core to surface. What once flowed steadily outward began to slow, not because conditions changed above, but because the reservoir below was steadily draining. As time passed, the interior cooled faster than that of larger worlds. Rock that had once moved with relative ease became more rigid. Convection, the slow circulation of material driven by heat differences, weakened. This motion matters because it keeps a planet responsive, allowing energy to redistribute instead of pooling and fading. On Mars, the gradients flattened. Warmth no longer rose as efficiently, and the system lost momentum. The core felt this change first. Early on, it had remained warm enough to sustain motion within its metallic layers. That movement had consequences far beyond the center of the planet. It powered interactions that influenced everything above, from the behavior of the crust to the structure of the atmosphere. As heat declined, motion slowed. Liquid metal thickened, circulation patterns weakened, and the processes tied to them began to fall out of sync. This loss of movement was not sudden. It unfolded across vast spans of time, each stage nearly indistinguishable from the one before. There was no collapse, no visible break. Instead, activity diminished by degrees. What had been dynamic became sluggish. What had been sluggish became still. The interior gradually surrendered its role as a sustaining force. With reduced motion came reduced interaction between layers. Energy became trapped rather than transferred. The crust settled into a quieter state, less fractured, less responsive to pressure from below. Pathways that had once allowed heat and material to reach the surface closed or narrowed. The planet's ability to renew itself diminished from within, even as conditions above demanded that renewal more urgently. This cooling reinforced every other vulnerability. Without internal heat to drive change, recovery from loss became impossible. Processes that depended on energy input weakened together, creating a cascade without drama. The planet still existed as a solid body, but its internal conversation had grown faint. Mars was becoming geologically passive. The effect of this shutdown extended outward in subtle ways. With the engine idling, surface features preserved themselves rather than evolving. Older structures endured with minimal alteration. Mars began to retain its history instead of rewriting it. Each layer of rock became a page that would no longer be revised by deep forces. The planet shifted from an active participant in its own shaping to a keeper of memory. This internal quiet also removed any possibility of reversal. Cooling is one direction only. Once heat escapes, it does not return. Mars did not suffer a single decisive failure. It simply lost the capacity to respond to gradual challenges. The world still turned, still orbited, still held form, but the processes that once balanced loss had slowed beyond effectiveness. By the time the engine truly fell silent, the outcome was already determined. External pressures continued, atmospheric thinning progressed, surface water retreated, and no deep force remained to counteract them. Mars had become a planet running on stored momentum alone. Its interior no longer drove change, no longer supported recovery, no longer contributed to survival. What remained was a world cooling from the inside out, stable in appearance, quiet in operation. The core had given all it could, and the surface settled into a long stillness shaped by what had already been lost. Mars continued onward, intact and unbroken, carrying the quiet consequence of having grown cold too quickly. The timing of disappearance is written quietly into stone. Long after the field itself vanished, its absence left a pattern that could be read. Ancient surfaces preserve orientations that point to an earlier alignment, while younger terrains do not. Lava that cooled before the loss recorded direction and strength. while flows that followed carry no such memory. The contrast between these ages allows a boundary to emerge, not as a single date, but as a narrowing window in deep time. Crater counts refine that window. Surfaces bearing magnetic signatures belong to an older era marked by heavier bombardment, while magnetically silent plains correspond to a later period when impacts were fewer. The overlap reveals a transition rather than a moment. The field weakened, then ceased, across spans measured in hundreds of millions of years. By the time the youngest unmagnetized rocks formed, the planet's internal dynamo no longer shaped its surroundings. Meteorites add another clue. Some fragments that originated on Mars carry remnant magnetism locked within their minerals. Their crystal histories indicate formation while a field still existed. Others, formed later, lack that imprint entirely. Together, these samples extend the timeline beyond any single site, confirming that the shutdown was global and enduring. The record converges from different materials and methods, all pointing toward the same, long, fading. This timing matters because it marks the last line of defense. Atmospheric loss had been underway already, but the disappearance of magnetic influence removed a second restraint. From that point forward, there was no mechanism left to divert charged particles before they interacted with the upper air. Gravity alone governed retention, and gravity was not sufficient. The change did not increase the force of loss, it removed the possibility of moderation. No impact compares to this outcome. Collisions can scar a surface and inject energy, but they do not persist. Even the largest leave after effects that diminish with time. The failure of the magnetic field altered conditions continuously. It allowed the sun to engage directly with the atmosphere every day, every orbit, without interruption. The scale of influence was planetary, and the duration was permanent. After the field failed, exposure became the default state. Charged particles reached altitudes where gases were already tenuous, and interactions intensified. Ionized atoms were lifted and carried away along magnetic lines embedded in the solar wind itself. Each escape was small, yet the pathway remained open. Loss no longer depended on circumstance, it became routine. This permanence changed the calculus of survival. Processes that might have compensated earlier could no longer keep pace. Even if volcanic sources released gases, even if brief warming occurred, escape would continue unchecked above. The atmosphere entered a regime where recovery required protection that no longer existed. The planet did not become uninhabitable at once. It became unable to prevent becoming so. The surface bears no scar that marks this shift. Valleys remained where they were, basins still cupped the land, and ice continued to move slowly. The transformation occurred overhead, silent and invisible from below. Mars became a world without an outer boundary, capable of turning energy aside. Space pressed closer, and the sky thinned as a result. From this stage onward, the future narrowed. Exposure persisted through every season and every cycle that followed. The planet continued to cool, the atmosphere continued to lighten, and surface water retreated further. Without magnetic influence, each of these trends reinforced the others. The loss was not dramatic, but it was decisive. When scientists trace the history back to this passage, they find no rival moment. Impacts punctuate the timeline, climate shifts alter the surface, volcanism rises and falls. None compare to the lasting consequence of this failure. With the magnetic field gone, Mars became permanently open, and the long conversation between its interior, its atmosphere, and space settled into silence. The loss that followed did not resemble destruction. It unfolded as a continuation, stretched thin across time. Once Mars stood fully exposed, its atmosphere began a long retreat that would last hundreds of millions of years. There was no surge in violence, no sudden acceleration. The same quiet processes kept working, day after day, orbit after orbit, lifting particles from the upper air and carrying them outward into space. This escape was gradual enough to escape notice from the surface. The sky did not vanish, it simply became lighter. Each generation of atmosphere was slightly thinner than the one before. Gases that reached high altitudes encountered energy from the sun that exceeded the planet's ability to hold them. Some drifted away as neutral atoms, others were ionized and guided outward along electromagnetic paths embedded in the solar wind. The mechanism mattered less than the consistency. Loss was always present, never interrupted. Over geological time, consistency becomes decisive. A process that removes only a small fraction each year can still erase an entire reservoir if allowed to continue long enough. Mars did not lack air because it lost everything quickly. It lacked air because it could not stop losing it at all. The balance never returned. Replacement remained insufficient. The atmosphere thinned not through catastrophe, but through patience. This is why the outcome feels quiet rather than dramatic. Nothing marked the point where loss became irreversible. Each stage felt similar to the last. The planet continued to turn, seasons still passed, dust still moved across the surface. Yet with each passing span of time, pressure decreased, temperatures shifted downward, and surface processes lost flexibility. Finality emerged, not from intensity, but from duration. Evidence of this escape is not confined to ancient rock. It is measured now, in the present. Orbiting spacecraft detect particles streaming away from Mars even today. Instruments observe ions caught by the solar wind, tracing paths that lead away from the planet. The rates are modest but unmistakable. The same slow leak that shaped the past remains active, still removing what little atmosphere remains. These measurements confirm continuity. Mars did not complete its transition and stop changing. It continues to lose air, though far less remains to take. The planet exists in a state of long aftermath, where the major transitions have passed but their consequences continue. Each escaping particle is a reminder that the process never found an endpoint. As the atmosphere diminished, its influence on the surface weakened further. With less air to transport heat, temperature extremes grew sharper. With lower pressure, liquid water became increasingly untenable. With reduced shielding, radiation reached deeper into the environment. None of these shifts required a trigger. They followed naturally from thinning skies. The phrase bleeding is fitting not because the loss was violent, but because it was continuous. Mars did not suffer a wound that closed. It experienced an opening that never healed. The leak was slow enough to appear manageable at every stage, yet relentless enough to remove nearly everything over time. Silence followed, not because activity ceased everywhere, but because the planet no longer had a medium through which to express it. In the end, the escape into space defined Mars's modern condition. Thin air, frozen water, and long-term stability emerged as consequences of prolonged loss rather than sudden failure. The planet remains intact, its surface preserved, its history readable. Above it, the atmosphere continues its faint departure, drifting away molecule by molecule, leaving behind a world that fades not through collapse, but through endurance stretched too far. Cold does not arrive as an invader. It settles when motion slows. On Mars, the retreat of water from the surface did not require a sudden drop in temperature. It followed naturally as air thinned, pressure weakened, and warmth became less reliable. Liquid water still appeared at times, but it could no longer remain exposed for long. What lingered sought shelter, moving downward into the ground or drifting toward regions where ice could persist without interruption. Underground became the first refuge. Beneath the surface, temperatures fluctuated less sharply, and trapped heat from the planet's interior offered limited stability. Water seeped into pores and fractures, freezing in place rather than flowing onward. Layer by layer, ice filled spaces once occupied by circulating liquid. These frozen reserves did not vanish. They remained present but immobilized, no longer part of a living surface system. At the same time, the poles began to gather what the rest of the planet could not hold. Seasonal frost transitioned into permanent accumulation. Snow and ice built slowly, compacting over long spans of time. Each cycle favored retention over loss. What reached these colder regions stayed. Polar deposits grew thicker, preserving water in a form that resisted evaporation and escape. The balance had shifted decisively toward storage rather than exchange. Between subsurface ice and polar caps, a new condition spread across Mars. Permafrost advanced outward from cold zones and downward from the surface. Soil that once thawed periodically became permanently frozen. This transformation altered the behavior of the ground itself. Materials that had once shifted, absorbed water, and responded to temperature now remained rigid. The land lost flexibility. As permafrost expanded, the surface entered a state of suspension. Chemical reactions slowed further. Weathering became dominated by dry processes. Without liquid water to dissolve, transport, and reshape materials, erosion lost efficiency. Features already carved remained largely unchanged. New ones formed only slowly, through wind or thermal stress. Mars began to preserve itself. The locking of the surface created a feedback that reinforced stability. Frozen ground prevented water from returning to circulation, even during brief warming. Meltwater pooled shallowly or refroze before penetrating deeply. The planet's exterior became resistant to change, guarding its existing forms while preventing new ones from emerging. Mars was not actively freezing everywhere at once. It was settling into a colder equilibrium. This phase did not erase signs of what came before. Valleys, deltas, and basins remained visible, their outlines intact beneath dust and ice. The difference lay in behavior rather than appearance. The surface no longer responded dynamically to the environment. It held its shape. Mars had become a world that remembered rather than reacted. Water still existed in abundance compared to what remained in the air. It simply changed state and location. Locked away in ice, it no longer moderated climate or transported energy. Its retreat removed one of the last agents capable of softening extremes. Temperature swings became sharper, and seasonal variation grew more severe without liquid buffers. This dominance of ice marked the close of surface habitability, not because water disappeared entirely, but because it withdrew from participation. Frozen water is stable, patient, and silent. It records time without altering it. Mars entered an era where change occurred primarily through accumulation rather than transformation. The takeover was complete when motion ceased to matter. With water immobilized and ground frozen, the surface settled into long-term stillness. Mars remained active in small ways, shaped by wind and dust, but its fundamental character had shifted. Ice held the planet in place. What followed would not erase this state, only continue it. A planet breathes through its surface, not in pulses that can be heard or seen, but through slow release, a steady exchange between what lies beneath and what surrounds it. Volcanoes are part of that breathing. They deliver more than fire and stone. They move gases from deep reservoirs into the open air, refreshing an atmosphere that would otherwise thin with time. Where this exchange continues, habitability remains possible. On Mars, volcanic activity once played this role with quiet persistence. Vast regions were reshaped by lava that spread gently across plains, cooling slowly and releasing gases as it went. These gases did not need to arrive in bursts. Their importance lay in consistency. Carbon dioxide, water vapor, and other compounds entered the sky gradually, reinforcing pressure and maintaining warmth. The atmosphere was not static, it was supported. As the interior cooled, this support weakened. Volcanic systems grew less frequent, their intervals stretching wider with each passing epoch. The heat required to melt rock and drive eruptions diminished. Magma chambers stalled, pathways sealed. What had once been a distributed network of release narrowed to isolated activity, then to long dormancy. The fading was uneven. Some regions quieted earlier than others. Large volcanic provinces continued to show signs of activity long after smaller systems had ceased. This staggered decline prolonged the process without preventing its outcome. Each pause between eruptions grew longer than the last. The sky received fewer additions. The balance that once held began to tilt more noticeably. Volcanic gases matter because they replenish what escapes. Without them, an atmosphere depends entirely on retention. Mars had already lost much of its ability to hold air. Once volcanism declined, it also lost its ability to replace it. The loss became one-directional. Air left, but nothing returned in sufficient quantity. This change affected climate in subtle ways. With fewer greenhouse gases entering the atmosphere, heat retention weakened further. Cooling at the surface reinforced cooling within the planet. The cycle closed in on itself. Each reduction made the next more likely. Recovery required an energy source that no longer functioned. Volcanic silence also meant chemical stillness. Reactions between rock, water, and gas slowed when inputs ceased. New minerals formed less readily. Surface chemistry became a record of past conditions rather than an expression of present ones. Mars shifted from a system that evolved continuously to one that preserved states already reached. There was no single eruption that marked the end. The last activity did not signal finality at the time it occurred. It simply joined a pattern of increasingly rare events. Only in hindsight does the silence become absolute. Once the planet crossed into a state where internal heat could no longer mobilize material, the possibility of atmospheric renewal disappeared. Even if other conditions had improved, there would have been no mechanism left to take advantage of them. Volcanism does not restart on a schedule. It requires sustained internal energy and motion. Mars no longer had either. The engine that could have lifted gases into the sky had shut down beyond repair. This is why volcanic silence carries such weight. It represents the closing of the last active pathway for recovery. Atmospheric loss continued, pressure continued to fall, ice continued to advance. Without eruptions, none of these trends could be countered from below. The surface remained calm, but the system as a whole lost flexibility. Mars did not fail because it lacked volcanoes entirely. It failed because they stopped at a time when they were still needed. Once they fell silent, the planet entered a state defined by endurance without renewal. What remained was a world shaped by earlier fire, now quiet, its atmosphere thinning under a sky that would never again be refilled. Nothing ended Mars all at once. There was no impact large enough to fracture the planet, no eruption vast enough to poison its skies overnight, no sudden darkness that rewrote its fate in a single moment. The transition unfolded without spectacle. Change accumulated quietly, layered gently atop earlier change until the planet found itself somewhere new without ever choosing to go there. Each shift on its own seemed manageable. A slightly thinner atmosphere altered temperatures by small degrees. A modest drop in pressure shortened the lifespan of surface water. Reduced volcanic output slowed the return of gases to the sky. None of these developments would have mattered much in isolation. Each could have been absorbed, adjusted to, perhaps even reversed under different conditions. Mars did not collapse under any single weight. It leaned slowly under many. Time played the decisive role. When changes unfold gradually, they rarely announce their significance. Millions of years passed between meaningful milestones. Processes overlapped rather than followed cleanly. Cooling in the interior weakened atmospheric renewal, just as atmospheric thinning weakened surface stability. Water retreated as pressure declined, and declining water further altered climate behavior. Every effect softened the planet's ability to respond to the next. Mars became a world governed by feedback rather than resilience. Loss reinforced loss. Cooling encouraged stillness. Stillness encouraged further cooling. As systems weakened, recovery required more energy than the planet could provide. What had once been fluctuations became trends. What had once been trends became conditions. There was no clear boundary separating before from after. Instead, Mars drifted across a threshold without noticing. Stability depends not only on having the right ingredients, but on keeping them within narrow limits. Once those limits are exceeded, returning becomes difficult even if conditions pause. Mars crossed several such limits over time. Each crossing reduced the range of futures available to it. This is what makes the collapse subtle. The planet continued to look solid and familiar. Mountains remained. Valleys stayed carved into the surface. Ice persisted. Dust storms still rose and fell. Mars did not appear broken. It appeared settled. Yet beneath that calm exterior, essential cycles had slowed beyond repair. The loss of flexibility mattered more than the loss of any specific feature. A world can endure thinner air, colder temperatures, or reduced water if it retains the ability to change. Mars lost that ability step by step. Each reduction in internal energy narrowed the options for response. Each decrease in atmospheric pressure limited surface processes further. Eventually, there were no pathways left that led back toward habitability. What followed was not chaos, but order of a different kind. Mars entered a stable but diminished state. Conditions stopped fluctuating widely. Extremes became consistent. The planet no longer hovered near balance. It settled into imbalance that could sustain itself indefinitely. This new equilibrium was quiet, predictable, and unyielding. Because no disaster marked the transition, no single moment can be identified as the end. The planet did not recognize when it passed the point of no return. The surface continued to record the environment faithfully, even as the environment itself lost the capacity to support complexity. Mars carried on, unaware that options were disappearing. This kind of ending leaves no obvious scar. It leaves a pattern. Scientists read that pattern today in layered rock, mineral chemistry, atmospheric remnants, and frozen water. Each record captures a piece of gradual decline rather than abrupt ruin. Together, they reveal a world that did not fail catastrophically, but comprehensively. Mars did not fall, it faded. Small changes stacked patiently until reversal was no longer possible. By the time the consequences became unavoidable, the causes were far behind in deep time. The planet had already crossed into a future shaped not by disaster, but by the quiet accumulation of irreversible steps. Rain did not disappear in a moment. It receded as conditions narrowed, then failed to return at all. In its absence, another force assumed control of the surface. Wind, once a secondary presence, became the primary agent of motion. Mars transitioned into a world where air, thin as it was, carried the responsibility of change. The atmosphere no longer supported clouds that could release sustained precipitation. Without rain to soften ground or transport sediment through flowing channels, the planet's energy found a different outlet. Pressure differences still formed as sunlight warmed some regions more than others. Temperature contrasts still drove circulation. Even a weakened sky retained the ability to move. That movement found purchase in loose material left behind by earlier eras. Dust became the medium through which Mars continued to evolve. Fine particles lifted easily from a dry surface, rising into the air and traveling vast distances. What water once moved downward and outward, wind now lifted and spread. The effect was slower but broader. Entire regions could be coated or stripped without a single drop falling. Dust storms emerged as a defining feature. They did not require violent winds, only persistence. Once particles entered the air, they absorbed sunlight and warmed the surrounding atmosphere, strengthening circulation and lifting even more material. Storms expanded gradually, sometimes encircling the planet, not as sudden disasters, but as extended events that altered light, temperature, and visibility for weeks at a time. These storms reshaped the surface without carving it. They scoured softer materials, exposing harder layers beneath. They filled low areas with drifting sediment, smoothing contrasts left by earlier activity. Over time, edges softened, details blurred. Mars did not erode into new forms so much as it settled into simpler ones. Erosion continued, but it took on a different rhythm. Instead of being episodic and directional, driven by flowing water, it became diffuse. Rock wore down through abrasion rather than dissolution. Chemical weathering slowed dramatically, replaced by mechanical grinding and redistribution. The landscape aged in place. Dust also acted as insulation. Layers accumulated unevenly, covering ice, shielding it from sunlight, then later exposing it again when winds shifted. This exchange created subtle cycles independent of liquid water. Mars developed a surface that could change appearance seasonally without changing state. Activity persisted, even as transformation slowed. The absence of rain removed one kind of noise from the planet. Rivers no longer announced themselves with fresh channels. Slopes no longer collapsed under sudden saturation. Instead, Mars expressed motion through suspension. Particles hung in the air, settled, and lifted again. The soundless choreography repeated endlessly, driven by solar heating and planetary rotation. This dryness did not mean inactivity. On the contrary, Mars remained engaged with its environment. Winds traced patterns across plains, sculpted dunes, and rearranged surface layers. Dust storms interacted with topography, creating localized effects that varied from region to region. The planet maintained complexity, but it was atmospheric rather than hydrological. Over time, this wind-dominated world reached a steady character. The surface became accustomed to redistribution rather than excavation. Features that survived did so because they resisted abrasion, not because they were reinforced by renewal. Mars learned to persist through endurance rather than change. Rain had once connected sky and ground directly, transferring energy downward. Wind redirected that exchange laterally, skimming the surface instead. The planet adjusted without protest. What mattered was not the loss of one process, but the adoption of another. Mars became dry, but it did not become still. In this phase, the planet revealed a new identity. Stripped of water-driven drama, it settled into a quieter form of activity. Dust replaced rain as the messenger between air and land. Motion continued without moisture. Mars carried on, reshaped gently by forces that required no liquid at all. Cold eventually becomes a constant. On Mars, that constant arrived gradually, settling into place as other forms of motion slowed or vanished. Temperature no longer hovered around thresholds that allowed frequent change. Instead, it stabilized at low extremes, defining the planet's surface with a clarity that left little room for variation. Warmth still appeared briefly, but it no longer shaped the overall character of the world. As the atmosphere thinned and water withdrew, the planet lost its ability to store heat. Without dense air to buffer energy, sunlight warmed the surface quickly during the day and released that warmth just as quickly when night returned. These sharp exchanges became routine. Mars no longer moderated its environment. It reacted directly to the sun, moment by moment. Seasonal cycles intensified under these conditions. Axial tilt still guided the march of seasons, but the effects grew harsher. Winters plunged deeper. Summers rose only modestly in response. Ice expanded and contracted more dramatically, advancing across the ground during long cold periods and retreating slightly when sunlight strengthened. These movements were not signs of recovery. They were oscillations around a new, colder baseline. Frozen ground became the norm rather than the exception. Permafrost extended across vast regions, locking soils into rigid states that resisted change. Where ice lay close to the surface, it sublimated slowly into the thin air, only to redeposit elsewhere as frost. This exchange created subtle textures and patterns, but it did not restore mobility. The cold governed every interaction. The deep freeze altered the planet's rhythm. Processes that once operated over short spans now required far longer to leave visible effects. Chemical reactions slowed to near stillness. Rocks fractured more readily under thermal stress, but those fragments accumulated in place instead of being carried away. Mars aged without rearranging itself. Despite the severity, the cold was not chaotic. It became predictable. Extremes repeated reliably, driven by orbital mechanics rather than internal variability. This regularity allowed the planet to settle into a steady state. Mars no longer drifted toward new conditions. It remained where it was, cycling through familiar patterns without escaping them. The atmosphere, now thin and dry, amplified these effects. With little moisture or pressure to dampen temperature changes, the surface responded directly to every shift in sunlight. Shadows grew colder, exposed ground warmed briefly, and the difference between the two defined local environments. These contrasts shaped frost formation, dust movement, and ice stability, but they did so within narrow limits. This long-term cold did not erase all activity. Winds still moved, dust still lifted, and ice still shifted at the margins. Yet none of these processes challenged the overall climate. They occurred within a framework that no longer allowed liquid water to persist or heat to accumulate. Mars had become climatically quiet. What distinguishes this phase is permanence. Earlier cold spells had been temporary, punctuated by warmer intervals that allowed partial recovery. This time, no such interval followed. The mechanisms that might have driven warming were gone. The planet was no longer cooling towards something new. It had arrived. The deep freeze marked the close of Mars as a flexible environment. From this point onward, change would be incremental and superficial. The planet could record variations, but it could not transform them into new states. Cold became the background condition against which all other processes played out. Mars settled into this climate without resistance. The surface adapted by becoming inert, preserving its shapes and features beneath layers of frost and dust. The sky adapted by thinning further, offering little insulation. Together, they formed a stable arrangement that could persist indefinitely. The planet continued to turn, bathed in sunlight, enduring a cold that no longer advanced or retreated. It simply remained. Not everything vanished when the surface fell silent. As conditions above hardened and cooled, the most enduring remnants of Mars withdrew downward, slipping beneath layers of rock and frozen soil. Below the reach of daily temperature swings in thin air, water found shelter. What survived did so quietly, preserved by depth rather than abundance. Subsurface ice became the dominant reservoir. It formed as water vapor, diffused downward and froze, filling pores and fractures, cementing grains together. In some regions, this ice reached astonishing thickness, extending for hundreds of meters. Protected from sunlight and insulated by overlying material, it remained stable long after surface ice thinned or shifted. This buried water was not mobile, but it was persistent. In certain places, conditions allowed something more complex. Heat lingering from the planet's interior, combined with pressure from overlying rock, created environments where ice could soften at its base. Salts mixed into the ground lowered freezing points, allowing pockets of briny liquid to persist without evaporating or boiling away. These zones were rare and isolated, but they existed beyond the reach of the harsh surface. Depth changed the rules. Pressure increased steadily underground, countering the instability that plagued exposed water. Temperatures varied less dramatically, rising gradually with proximity to the interior. In these layered conditions, water no longer needed to endure direct contact with the sky. It could remain in place for long spans of time, shielded from the forces that stripped the surface bare. This survival did not imply abundance or accessibility. Any liquid present underground existed slowly, confined by rock and ice, moving only under subtle gradients. It did not flow freely or reshape landscapes. Instead, it waited. Mars did not become wet below ground. It became archival. The planet's crust turned into a storage medium. Each layer trapped chemical signatures, isotopic ratios, and mineral formations that recorded earlier conditions. Subsurface ice locked in gases from the ancient atmosphere, preserving a record of its composition at the time of freezing. Water that remained in liquid form interacted gently with surrounding rock, leaving traces that reflected long-term stability rather than rapid change. This preservation made Mars unique among rocky planets. Earth's active interior constantly reshapes its surface, recycling crust and erasing evidence of its earliest environments. Mars, having cooled more quickly, lacked this continuous renewal. What retreated underground often stayed where it settled. The planet became a sealed archive, holding chapters of its history intact beneath a quiet surface. That archive extends beyond water alone. Organic molecules, delivered by meteorites, altered by ancient chemistry, could persist longer underground than they ever could on the surface. Radiation weakened with depth, slowing degradation. In this protected space, time moved differently. processes that lasted moments above could endure for eons below. The existence of these hidden reservoirs does not change the planet's present condition. Mars remains cold, dry, and largely inert at the surface. Yet beneath that stillness lies continuity. The planet did not lose everything. It stored what it could, preserving remnants rather than sustaining systems. This subsurface survival reframes the story. Mars did not simply end, it transitioned from expression to memory. The features visible from orbit tell only part of that story. Beneath them, ice and trapped water hold quieter records, layered carefully by a planet that learned to keep its past when it could no longer support its future. Mars continues to carry this archive forward. Each passing year adds little change above, but below, conditions remain stable enough to preserve what was once active. The planet rests, not empty, but sealed. What survived did so by retreating inward, becoming part of a long-held record that endures without alteration, waiting beneath the frozen ground. Life does not require perfection, but it does require time. On Mars, the conditions that once supported water and chemistry did not disappear instantly. They narrowed. Habitability became something that arrived briefly, then withdrew, then returned in smaller forms. These intervals are known as habitable windows, periods when conditions align just long enough for biology to persist, even if it cannot fully establish itself. Early Mars offered something closer to permanence. Water remained on the surface for extended spans, chemistry cycled, and energy gradients stayed available. Life, if it emerged at all, would not have needed to hurry. It could adapt, spread, and diversify. As the planet changed, those steady conditions fragmented. Habitability shifted from being continuous to conditional. Surface environments were the first to suffer. As pressure fell and radiation increased, exposed water became unreliable. Ultraviolet light reached ground level more easily, breaking apart organic molecules faster than they could be replaced. Temperature swings intensified, pushing conditions beyond tolerance for most known biological systems. Even resilient life struggles when liquid water cannot remain stable at the surface. This did not mean the surface became instantly sterile. For a time, short-lived wet periods may have supported brief biological activity. Meltwater from ice, groundwater release, or localized warming could create transient habitats. These moments, however, were fleeting. They did not last long enough to sustain complex ecosystems or allow recovery between episodes. Life could arrive, persist briefly, and then be forced back into dormancy or retreat. As surface habitability faded, depth became refuge. Beneath layers of rock and ice, conditions changed more slowly. Radiation weakened, temperatures stabilized, pressure increased. Chemical energy remained available through interactions between water and minerals. These environments did not fluctuate as violently as the surface. They offered continuity where the exterior no longer could. Life, if present, would have followed that gradient downward. Microbial systems are especially well suited to such transitions. On Earth, similar organisms thrive kilometers beneath the surface, isolated from sunlight, yet sustained by geochemistry alone. Mars offered comparable niches for a time. Water trapped underground, whether frozen or briny, provided a medium for slow metabolic processes. The longest-lasting habitats would have been those least connected to surface chaos. Deep fractures, pore spaces in rock, and zones warmed slightly by residual heat offered stability. These environments did not promise abundance, they promised endurance. Life adapted to such conditions does not expand quickly or visibly. It persists quietly. The difference between habitability and life becomes important here. A planet may no longer be broadly habitable while still hosting isolated living systems. Mars appears to have crossed that threshold. Its surface could no longer support life as an ongoing presence. Yet beneath, conditions remained tolerable for far longer. The planet did not eliminate possibility, it confined it. Eventually, even these refuges would face limits. As the interior cooled further and chemical gradients weakened, available energy diminished. Habitable windows below ground narrowed as well. Life, if present, would have slowed accordingly, retreating into increasingly marginal spaces. Persistence would have depended on efficiency rather than expansion. This gradual constriction matters more than a sudden end. Mars did not offer a single moment of extinction. It offered a long corridor of diminishing opportunity. Life could survive by adapting to each narrowing condition, but only up to a point. When energy input and water availability fell below critical thresholds, survival would have required states approaching stasis. In this way, Mars becomes a lesson in time rather than catastrophe. Permanent habitability supports complexity. Temporary habitability tests resilience. The planet transitioned from one to the other, then continued narrowing the margin. Life may have endured not because conditions remained generous, but because change allowed just enough continuity to persist quietly. For a while, below a surface that had already moved on, time behaves differently on a quiet planet. On Mars, change slowed early, then slowed again, until it approached stillness. Without the constant reshaping forces that transform more active worlds, the surface began to act less like a canvas and more like an archive. What happened once remained visible long after the conditions that created it were gone. Mars preserves its past because it stopped rewriting it. The planet cooled quickly, its interior losing the heat needed to drive continuous renewal. With limited tectonic movement, the crust remained largely intact. Layers of rock settled where they formed, undisturbed by recycling. Once a feature appeared, it was rarely erased. Instead, it aged in place. Water had once shaped the landscape decisively. Rivers carved channels, lakes filled basins, deltas spread sediments into standing water. When liquid water retreated, these features did not vanish. Without flowing currents to soften edges or transport material away, their forms endured. Channels remained etched into the ground. Shorelines stayed traced along crater rims. Mars retained the outlines of processes that had ended. Wind altered the surface, but it did so gently. Dust smoothed details without destroying them. Erosion by air redistributed material rather than breaking down structures entirely. The result was preservation beneath a thin veil. Ancient terrain persisted, visible from orbit after billions of years. Mars became a world where past and present coexisted on the same surface. This preservation contrasts sharply with Earth. Our planet remains geologically alive. Its interior heat drives plate tectonics that continuously reshape the crust. Oceans subduct old seafloor and generate new rock in its place. Mountains rise and erode, sediments cycle, and surfaces renew. Water flows everywhere, dissolving, transporting, and reworking material. Earth erases its early chapters as part of remaining active. What Earth gained in habitability, it lost in memory. The environments that may have hosted the earliest life are largely gone, recycled into the mantle, or altered beyond recognition. Clues survive only in fragments, transformed and incomplete. The The surface tells a story dominated by recent chapters, while earlier ones fade into obscurity. Mars followed the opposite path. It lost long-term habitability, but in doing so, it preserved its geological record. Without plate tectonics to recycle crust and without persistent liquid water to rework terrain, ancient surfaces remained exposed. Impact craters accumulated rather than being erased. Volcanic plains stayed visible long after eruptions ceased. The planet froze its history into place. This makes Mars uniquely valuable as a record of early planetary processes. Features that disappeared on Earth remain legible there. Valley networks record how water once flowed. Mineral deposits preserve chemical interactions that require specific conditions. Even the atmosphere left traces within rocks and ice that still sit near the surface. Mars holds snapshots of stages Earth passed through but no longer remembers clearly. The planet does not preserve everything perfectly. Dust covers details, impacts modify terrain, and slow erosion continues. Yet the rate of change is so low that features billions of years old remain identifiable. Mars functions as a time capsule not because it is unchanged, but because it changes so slowly. This stillness allows scientists to read sequences rather than guesses. Layers remain stacked in order. Craters overlap predictably. Ancient shorelines align with past climate models. Mars offers continuity, a rare quality among rocky planets. It allows the past to remain present without being overwritten. In losing the forces that sustain life, Mars gained the ability to remember. The same processes that made Earth dynamic also made it forgetful. Mars chose the opposite fate by necessity rather than intention. It became a planet where history stayed visible, etched across its surface and locked beneath it. What Earth erased through renewal, Mars kept through stillness. Earth did not escape the same early challenges faced by Mars. It formed in the same neighborhood, endured the same bombardment, and began with many of the same raw ingredients. Yet its path diverged steadily, guided by differences that accumulated quietly rather than dramatically. From the inside out, Earth maintained qualities that allowed it to respond, adapt, and recover when conditions shifted. Size played a foundational role. Earth retained more heat from its formation, storing energy deep within its interior. That heat did not dissipate quickly. It continued to circulate, driving movement long after smaller worlds had cooled. Internal warmth kept rock mobile, allowed pressure to build, and sustained the processes that connect interior and surface. Earth's engine never lost momentum at the critical moment. This enduring energy powered plate tectonics, a slow but persistent reshaping of the planet's exterior. Plates drifted, collided, and separated, recycling crust instead of letting it stagnate. Old surfaces were pushed downward and remade, while new ones emerged elsewhere. This motion prevented the planet from becoming locked in place. It allowed Earth to adjust continuously rather than preserve static states. Plate movement also mattered for the atmosphere. Subduction carried carbon and water into the mantle, while volcanic activity returned them to the surface. This exchange regulated climate over vast spans of time. When temperatures rose, certain processes accelerated. When temperatures fell, others took precedence. Earth's climate remained dynamic, guided by feedback that prevented extreme drift in either direction. Magnetic protection added another layer of resilience. Earth's core remained active, with circulating liquid metal sustaining a strong magnetic field. This field diverted much of the solar wind, shielding the atmosphere from direct stripping. While some loss still occurred, it happened slowly enough for replacement to match it. Air stayed close. Pressure remained stable. The sky endured. Water followed this stability. Oceans persisted, acting as reservoirs that moderated temperature and distributed heat globally. Liquid water did not merely shape the surface, it buffered change. It absorbed energy, released it gradually, and supported chemistry that could continue uninterrupted for billions of years. Earth never lost the ability to keep water where it mattered. These systems reinforced one another. Internal heat sustained tectonics. Tectonics sustained atmospheric balance. Atmospheric balance sustained liquid water. Liquid water supported climate regulation. Together, they formed a network that absorbed shocks instead of amplifying them. Earth did not avoid change. It survived change by remaining flexible. When challenges arose, Earth adjusted rather than narrowing its options. Cooling in one region was offset by activity elsewhere. Loss in one system triggered compensation in another. This capacity for renewal prevented the planet from crossing thresholds that could not be undone. Earth never became trapped in a single outcome. Mars lacked this margin. Its smaller size led to faster cooling. Its interior lost energy before recovery pathways could solidify. Without sustained tectonics, its surface froze into place. Without lasting magnetic protection, its atmosphere thinned. Without atmospheric pressure, water retreated. Each loss constrained the next. Earth stayed alive not because it was spared difficulty, but because it retained the means to respond. Its systems remained interconnected, able to exchange energy and material across scales. Life emerged into an environment that continued to support complexity rather than merely allowing it briefly. This divergence was not predetermined, but once it began, it compounded. Earth preserved activity at the core, motion at the surface, and protection above. Mars lost them one by one. The difference was not a single advantage, but the persistence of many small ones. Earth remains dynamic today, for the same reason it did not follow Mars. Its engine continues to run, its surface continues to renew, its sky continues to protect. Life did not hold Earth together. Earth held life by staying alive itself. Some changes allow retreat, others do not. On a planet, the difference lies in thresholds, boundaries that can be approached gradually, but crossed only once. These are not lines etched into space, but conditions embedded in physics and time. When passed, they alter what is possible afterward, no matter how slowly they were reached. Mars approached several such thresholds over its lifetime. None of them announced themselves when crossed. Each appeared ordinary at the moment, indistinguishable from earlier stages. Atmospheric pressure declined without signaling a final limit. Internal heat diminished without a clear endpoint. Water retreated without marking the last moment of stability. Yet, together, these shifts carried Mars beyond states it could not recover. One threshold involved pressure. Liquid water requires not only warmth, but enough atmospheric weight to remain stable. As pressure dropped, surface water became increasingly rare, then episodic, then effectively impossible. Once average conditions fell below this limit, even brief warming could not restore long-lived liquid water. The planet could not return to surface habitability because the basic requirement had been lost. Another threshold lay deeper. In the interior, planetary engines depend on sustained heat and movement. When internal circulation slows beyond a certain point, magnetic protection weakens irreversibly. Without a magnetic field, atmospheric escape accelerates. Even if gases are added later, they cannot be retained efficiently. Mars crossed this boundary when its core cooled enough to halt organized motion. From that point forward, exposure was permanent. A third threshold involved renewal. Active worlds continuously replenish what they lose. Mars gradually lost its ability to do so. Volcanic output declined below the level required to balance atmospheric escape. Once renewal fell behind loss, the system entered a new regime. Every year led to less capacity for the next. Recovery required energy that no longer existed. These thresholds were interconnected. Falling pressure affected water. Loss of water altered climate. Climate shifts reinforced cooling. Cooling weakened internal dynamics. Internal decline removed magnetic protection. Each step narrowed the window for reversal. The planet did not cross a single line. It crossed several, each reducing the effectiveness of any remaining pathways back. Timing determined the outcome. Had Mars retained its internal heat slightly longer, its magnetic field might have persisted through a critical period. Had volcanism remained active while the atmosphere thinned, pressure might have stabilized at a survivable level. Had water retreated more slowly, it might have buffered climate long enough to preserve surface conditions. None of these delays occurred at the needed moment. Planetary evolution is not only about what exists, but when it exists. Mars possessed the necessary ingredients early on, but they did not overlap long enough. Heat faded as the atmosphere thinned. Protection failed as renewal weakened. Water retreated as pressure dropped. Each system gave way while others were already compromised. The sequence mattered as much as the components themselves. Once past these points, no external change could undo the result. Later volcanic eruptions could not rebuild a stable atmosphere. Local warming could not sustain liquid water. Subsurface reservoirs could not influence surface climate. Mars entered a future with limited options, defined by stability without flexibility. The point of no return did not arrive in an instant. It emerged gradually, distributed across millions of years. By the time it could be identified, it had already passed. Mars continued evolving afterward, but within a much narrower range of states. This is how planets end without ending. Not through destruction, but through convergence. Mars crossed thresholds quietly, one after another, until the combined effect closed the door on recovery. What remained was not a dead world, but a settled one, shaped decisively by timing that allowed just enough change to occur, but never enough to reverse course. The span of change stretched far beyond any single age. Mars did not decline within a lifetime, or even within a recognizable era. Its transformation unfolded across hundreds of millions of years, a duration so vast that individual moments lost significance. Each stage blended into the next, smoothing edges until beginnings and endings dissolved into continuity. On such timescales, change rarely announces itself. What alters by fractions over millions of years appears stable when viewed from within. A slightly thinner atmosphere feels the same as before. A marginally colder climate does not register as loss. Water retreating by small increments leaves landscapes largely familiar. Mars drifted through these conditions without pause, never experiencing a day that felt markedly different from the one before. This slowness explains why decline remained invisible. Processes that move to gradually resist perception. Even dramatic outcomes can arise from steps so small they escape notice. On Mars, nothing accelerated sharply enough to draw attention. Instead, each system weakened just enough to place strain on the next. The planet did not feel itself changing. It simply continued forward. Geological records capture this pace with patience. Layers form thinly, separated by time rather than texture. Crater counts shift subtly. Mineral signatures evolve slowly. These traces do not point to a crisis, but to duration. They tell of persistence without recovery, of movement without reversal. The atmosphere thinned at rates measured in atoms rather than storms. Water retreated basin by basin rather than river by river. Heat escaped millimeter by millimeter through rock. Each process required millions of years to matter, yet once complete, its effect shaped everything that followed. The planet aged without incident. Silence accompanied this fading. No single sound marked the passage from warm to cold, from wet to dry. Mars did not roar or fracture. It cooled quietly, its systems decelerating together. Geological silence does not imply inactivity, but the absence of suddenness. Change became a background condition rather than an event. This quiet progression complicates interpretation. It tempts one to search for a cause dramatic enough to match the outcome. Yet the outcome arose precisely because nothing dramatic intervened. Had disruption arrived, it might have reset systems or altered sequences. Instead, Mars followed its internal clocks faithfully, each ticking down without interruption. The length of this decline also allowed preservation. Because change unfolded slowly, features formed early remained legible long after they stopped forming. The surface held memory while the interior cooled. Mars carried its history forward even as it lost the means to add new chapters. Slow change narrows options gradually. At each moment, alternatives still seem available. It is only in hindsight that missed opportunities become clear. Mars passed through stages where recovery might have been possible, yet nothing compelled that recovery to occur. The window closed incrementally, not decisively. By the time the decline became unmistakable, it was already complete in its essentials. The planet had settled into a new mode of existence. Air remained, but thin. Water persisted, but frozen or hidden. Motion continued, but limited. Mars did not cease evolving. It simply evolved within tighter constraints. This extended fading distinguishes Mars from worlds that end abruptly. There was no trauma to survive, only endurance without renewal. The planet remained intact and recognizable throughout. Its loss was not of form, but of capacity. Hundreds of millions of years passed as Mars transitioned from a responsive world to a settled one. The process did not hurry, and it did not pause. In geological silence, the planet drifted into stability, carrying the long memory of how slowly endings can arrive when nothing interrupts them. The world that remains is quiet in a way that feels complete. Mars today exists in a state defined not by absence, but by balance. What it has lost, it has finished losing. What remains consistently. The planet has settled into itself. Its air is thin, stretched lightly over the surface like a fragile veil. Pressure is low enough that sound travels poorly, winds whisper rather than roar, and exposed water cannot persist. The atmosphere still moves, still circulates, still responds to sunlight, yet it no longer serves as a reservoir of warmth or protection. It is present, but it no longer carries weight in the planetary system the way it once did. Water is abundant in form, but not in function. Ice dominates the landscape, locked into polar caps, layered beneath dust, and embedded within the crust. It does not flow. It does not cycle freely between states. Instead, it rests where it has settled, preserved by cold and pressure. Seasonal frost may appear and vanish, but the deep stores remain unchanged. Water survives, but it does not participate. The surface reflects this stillness. Valleys, deltas, and basins remain etched across the planet, their shapes sharply defined by the lack of erosion that would otherwise soften them. Rock remains exposed for vast spans of time. Dust shifts slowly, rearranged by wind rather than reshaped by water. Mars wears its history openly, with little to obscure it. Temperature varies, yet within narrow bounds, cold dominates. Daytime warming fades quickly after sunset. Nights plunge deeply. Seasonal changes arrive reliably, governed by orbit and tilt rather than internal dynamics. These swings do not lead to transformation. They repeat, cycle after cycle, without altering the larger state of the planet. Mars experiences weather without evolution. This stability defines modern Mars more than any individual feature. The planet is no longer moving toward a new condition, it is maintaining one. Processes that once interacted dynamically now operate in isolation. Wind moves dust, ice sublimates and redeposits, radiation strikes the surface. None of these processes feed into a system that can change itself meaningfully. Lifelessness on Mars is not violent, it is calm. The environment is harsh by terrestrial standards, yet consistent. There are no sudden extremes, no runaway feedbacks, no accelerating collapse. The planet reached its endpoint gradually and now remains there. Its silence is not the silence of devastation, but of completion. From orbit, Mars appears striking and complex. Color variations trace mineral composition. Polar caps gleam. Dust storms rise and fade. There is motion, but it does not accumulate toward novelty. The planet circulates energy without building new structures. It is active within limits it will not escape. This condition allows Mars to persist indefinitely. Without oceans to evaporate or atmospheres to lose rapidly, the planet changes very little over immense timescales. It has reached a configuration that is self-sustaining, though barren. Stability has replaced adaptability. Mars today is not a ruin. It is a resolved state. Its processes are slowed, its systems simplified, its pathways narrowed to a few reliable motions. The planet has finished transitioning. What remains is what will remain for a very long time. In this sense, Mars is at rest, not inert, not frozen entirely, but settled. The forces that once drove its transformation have spent themselves. The planet continues to turn beneath the sun, thin air drifting, ice holding firm, dust traveling patiently across ancient ground. Mars endures as a quiet world, stable, lifeless, and complete in its stillness. Existence does not require life. Mars demonstrates this distinction with clarity. The planet continues to turn, absorb sunlight, and exchange energy with space, yet it does so without the capacity to support living systems. What remains is not absence, but separation. Geological activity and habitability are not the same condition. Even when they once overlapped, Mars still functions as a physical body. Its crust responds to temperature changes. Winds move dust across plains and into basins. Ice shifts subtly beneath seasonal cycles. These are expressions of activity, measurable and ongoing. They reveal a world that has not stopped, only simplified. Motion persists where energy gradients still exist. Habitability, however, depends on more than motion. It requires environments that remain stable long enough for chemistry to organize itself, adapt, and continue. On Mars, those requirements are no longer met at the surface. Pressure is too low, radiation too intense, temperature swings too sharp. Water cannot remain liquid in open contact with the air. These limits are not temporary conditions. They are structural. The difference becomes clearer when considering scale. Geological activity can operate with minimal resources. It can continue under extreme cold, thin air, and isolation from internal heat. Habitability demands overlap. Liquid water must coincide with usable energy and chemical continuity. Mars once held that overlap. It no longer does. This is why Mars is not dead in the way a machine breaks. Nothing has failed catastrophically. The planet still behaves according to physical law. It responds predictably. Its systems remain coherent. What it lacks is the capacity to sustain complexity beyond a narrow, inert range. Life does not simply require presence, it requires margin. On Mars, that margin disappeared gradually. Conditions tightened until survival would require dormancy rather than metabolism. Even resilient microbial systems depend on periodic access to liquid water and chemical exchange. Mars no longer offers those consistently at the surface. The subsurface, sheltered and insulated, may still hold environments where water remains trapped and chemistry proceeds slowly. These niches, if they exist, are isolated and marginal. They do not interact with the broader planet. They do not influence climate or reshape terrain. They persist without spreading. A world sustained by such conditions is not alive in any planetary sense. It is enduring rather than living. This distinction defines a quiet form of planetary death. Mars did not lose form or motion. It lost responsiveness. It can no longer adjust its environment to maintain conditions favorable to life. The feedback loops that once stabilized climate and water have broken. What remains is balance without adaptability. The word death often implies suddenness or destruction. Mars offers neither. Its transition unfolded slowly, leaving the planet intact. The surface remains complex and legible. The atmosphere remains present, though thin. Ice remains abundant. None of these things signify vitality on their own. Planetary death, in this sense, is not an event but a state. It is reached when change no longer creates opportunity. Mars reached that state when its systems ceased to reinforce one another in ways that allow habitability to persist. From that moment onward, life became unsupported, even if traces endured. Mars still exists as a world, complete and self-consistent. It remains a participant in the solar system, influenced by gravity, sunlight, and time. What it no longer participates in is the dynamic cycle that supports life. This is the quiet definition. A planet may continue indefinitely without being alive. Mars stands as an example of that outcome. Not destroyed, not inert, simply settled beyond the conditions that allow life to be more than a memory held in stone and ice. Revival implies return, a movement back toward an earlier state. For planets, that idea encounters firm limits. Mars today is not simply paused. It occupies a configuration shaped by losses that altered the range of what is physically possible. Understanding why restoration cannot proceed requires accepting the planet as it is now, not as it once was. Mars functions as a closed system in practical terms. Energy enters primarily from the sun, and matter leaves slowly to space. What remains inside is finite. Over time, critical components were redistributed into forms that no longer participate in surface processes. Water moved underground or froze permanently. Atmospheric gases escaped or became locked into minerals. Heat dissipated into space. These were not temporary rearrangements. They were transitions to stable endpoints. Rebuilding an atmosphere illustrates the challenge. To restore surface pressure sufficient for liquid water, enormous quantities of gas would be required. Mars does not possess accessible reserves of this magnitude. Volcanism no longer supplies new material to the sky, and existing compounds are bound tightly within rock or ice. Releasing them would require energy far beyond any natural process still operating on the planet. Even if gas could somehow be added, retention would remain a problem. Without a strong magnetic field, the upper atmosphere would continue to interact directly with the solar wind. Escape would resume as it has for billions of years. Any partial thickening would be temporary, thinning again over geological time. Restoration would require not only adding material, but reinstating protection that the planet no longer generates. Heat presents a similar barrier. Mars cannot be warmed from within. Its interior engine has cooled beyond revival. External warming could raise surface temperatures briefly, but without pressure and atmospheric insulation, heat would dissipate rapidly. Seasonal changes already demonstrate this limitation. Warmth arrives and departs without altering the long-term state. Water, often imagined as the key to revival, faces multiple constraints. Ice exists in abundance, yet converting it into persistent surface liquid requires both warmth and pressure. Without sustained atmospheric support, water exposed at the surface would boil or freeze, then disappear. Subsurface water, where it exists, remains isolated and slow, unable to influence global conditions. These limitations reveal why Mars cannot be restarted like a machine. Planets are not assemblies of replaceable parts. Their states emerge from interactions across time. Once certain pathways close, reopening them demands energy and material beyond what the system contains. Mars has passed those thresholds. This does not mean the planet is fragile or degraded. It means it has reached equilibrium. Closed systems naturally evolve towards states that require the least ongoing input. Mars arrived at such a state long ago. Its present configuration is self-sustaining precisely because it no longer supports complex cycling. Any attempt to alter that state would have to overcome not only physics, but duration. Changes would need to persist for millions of years to matter. Temporary modifications would fade as the underlying constraints reasserted themselves. Mars would return to its settled condition. The idea of revival often reflects terrestrial thinking, where environments are actively maintained by biological and geological feedback. Mars no longer possesses those feedbacks. It is governed by simpler balances that resist intervention. What appears empty is actually complete. This completeness carries its own value. Mars preserves what it has become with remarkable stability. Its surface, climate, and internal structure are not in flux. They are resolved. Restoration would not only be difficult, it would require undoing the very processes that now hold the planet together. Mars remains a world, but it is a world defined by closure. Its systems have finished transitioning. Energy flows through it without reshaping it. Matter rests in long-term storage. The planet continues to exist within narrow, durable boundaries. Revival is not absent because of technological limits alone. It is absent because the planet has already chosen its outcome through physics and time. Mars cannot be returned to what it was, not because it is ruined, but because it is complete as it is, a closed system carrying the final form of a long planetary journey. Mars continues to draw attention not because it promises rescue or revival, but because it offers clarity. Scientists return to it again and again for what it reveals about planets, not for what it might become. Mars is not studied as a cautionary tale filled with drama. It is studied as a record, calm and precise, showing how planetary systems behave when time is allowed to run uninterrupted. The value of Mars lies in its honesty. It shows what happens when a world loses key capabilities without interruption or rescue. There is no mystery force hiding in the background. No catastrophic ending needs to be imagined. The processes that shaped Mars are familiar ones, operating at different scales and tempos. Studying them allows researchers to separate coincidence from consequence and possibility from inevitability. Mars offers a lesson rather than a warning because it does not accuse. It does not suggest that all planets must share its fate. Instead, it shows how outcomes diverge based on structure, timing, and internal resilience. By examining where Mars differed from Earth, scientists gain a clearer understanding of why Earth survived as it did. Comparison sharpens insight without assigning moral weight. Planetary survival is not defined by avoiding loss, but by sustaining balance. Mars demonstrates how fragile that balance can be when key systems weaken together. Internal heat, atmospheric retention, magnetic protection, and surface renewal are not luxuries. They are stabilizers. When one fails, others are placed under strain. Mars allows scientists to trace these relationships cleanly, without interference from ongoing renewal. Because Mars stopped changing quickly, its evidence remains accessible. Ancient terrains lie exposed, chemical signatures remain legible, crater records stay intact. This preservation makes Mars a natural laboratory for studying early planetary conditions, including those Earth has erased through its own activity. The past remains visible rather than buried. By studying Mars, scientists learn to recognize thresholds. They see where gradual change becomes irreversible. They observe how slow losses accumulate into decisive transitions. These insights apply beyond Mars itself. They inform how other rocky planets might evolve, including those orbiting distant stars. Mars becomes a reference point for understanding planetary longevity across the universe. This work is not driven by fear. It is driven by curiosity and precision. Mars allows questions about planetary futures to be grounded in evidence rather than speculation. It shows how long stability can persist after habitability fades, and how planets settle into enduring states that are neither violent nor empty. Reading Mars also sharpens perspective on Earth. Differences stand out more clearly when placed beside a world that followed another path. Earth's activity appears not inevitable, but contingent. Its renewal systems appear not guaranteed, but maintained. Mars gives context rather than contrast alone. Importantly, Mars reminds scientists that planets do not fail. They transition. Each world follows physical rules toward outcomes shaped by initial conditions and ongoing interactions. Mars followed its rules faithfully. That fidelity makes it valuable. It is reliable precisely because it is finished changing in essential ways. As exploration continues, new details add nuance without altering the core story. Subsurface ice, mineral diversity, atmospheric escape measurements, and surface chemistry all refine understanding. Mars does not overturn its narrative, it deepens it. Scientists keep studying Mars because it answers questions patiently. It does not rush to conclusions or obscure its past beneath activity. It allows careful reading. In doing so, it helps researchers understand not only what happened to one planet, but how planets endure, adapt, or settle across deep time. Mars remains a quiet teacher. Its lessons are not dramatic, but enduring. By listening closely to what it preserved, scientists learn how worlds change, how survival is sustained, and how the future of planets is written long before it becomes visible. Margins decide outcomes long before results appear. On Mars, those margins were narrow, but they existed. For a time, the planet occupied a rare balance where water could remain liquid, air could linger, and internal energy could still respond. Nothing about that balance guaranteed permanence, yet it lasted long enough to leave unmistakable traces of habitability across the surface. Mars came close because its ingredients aligned briefly. Internal heat persisted long enough to drive volcanism. Atmospheric pressure remained sufficient to allow standing water. Magnetic protection endured through a crucial early interval. These conditions overlapped rather than arriving in isolation. Rivers flowed while air still pressed down on the surface. Lakes remained while chemistry had time to settle. The planet did not merely experience wet moments, it sustained environments. The closeness lies in duration rather than intensity. Mars did not need more extreme conditions, it needed more time. A slightly thicker atmosphere retained slightly longer. A magnetic field sustained slightly deeper into its cooling. Volcanic activity extended marginally farther into the planet's middle age. Each small extension could have reinforced the next. Instead, the margins aligned just short of permanence. Internal heat declined as atmospheric protection weakened. By the time renewal began to matter most, the systems that could provide it were already fading. Mars did not miss habitability by vast margins. It missed it by timing, measured in millions of years, a brief interval in planetary terms. These small margins shaped everything that followed. Once pressure dropped below a critical range, water behavior changed irreversibly. Once internal circulation slowed beyond recovery, protection from space weakened permanently. Each threshold crossed removed a future option. Mars lost possibilities quietly, one by one, without dramatic markers. This closeness often invites comparison to Earth, yet proximity can mislead. Near Earth conditions do not produce Earth outcomes. Similar size, similar materials, and similar starting points do not guarantee similar futures. Mars demonstrates how sensitive planetary systems are to initial differences that appear minor but compound over time. Earth remained just far enough above critical thresholds to preserve flexibility. Mars remained just below. That distinction was enough. Earth's internal engine continued long enough to sustain tectonics. Mars cooled too quickly. Earth's atmosphere retained density through critical eras. Mars thinned at the wrong moment. Earth's systems reinforced one another. Mars's systems weakened in sequence. Near Earth is not Earth because survival is not binary. It depends on overlap, timing, and reinforcement. A planet may appear habitable by many measures, yet still fail to maintain those conditions. Mars met many criteria briefly, but not long enough for resilience to form. This closeness adds weight to Mars's record. Its surface does not describe an alien world that never had potential. It describes a world that approached stability and then lost it. The valleys and sediments are not anomalies. They are evidence of success that nearly endured. Mars almost made it because planetary survival is difficult, even when conditions seem favorable. The difference between enduring and fading can be subtle, a single system weakening slightly faster than another. A protective field failing just before renewal becomes critical, a margin crossed without notice. That is what makes Mars compelling. It was not doomed from the beginning. It was viable, active, and responsive for a meaningful span of time. Its failure was not inevitable, but neither was its survival guaranteed. The outcome arose from narrow margins that did not forgive delay. Mars remains close in memory because it was close in reality. Its fate was decided not by extremes, but by small differences that accumulated quietly. In those differences lies the lesson of a world that almost made it, and the understanding that proximity to success does not ensure arrival. Mars continues its path around the Sun without interruption. Its orbit is steady, predictable, unchanged by what the planet has lost. Each revolution traces the same ellipse through space, year after year, era after era. From a distance, nothing about that motion suggests failure. It looks complete, almost serene, a world fulfilling the simplest requirement of existence by remaining where it is. Yet within that constancy lies a profound isolation. Mars moves alone through time, detached from the cycles that once connected its surface, sky, and interior. There are no processes left that rebuild what erosion or escape removes. No deep engine waits to reawaken. The planet does not prepare for another phase. It maintains the one it reached. Loneliness, at a planetary scale, is not emotional. It is structural. Mars no longer participates in exchange with itself. Heat does not circulate upward in meaningful amounts. Gases do not cycle between interior and atmosphere. Water does not travel freely between surface and sky. These pathways once tied the planet together. Their absence leaves Mars compartmentalized, each part operating without reinforcing the others. The surface reflects this separation. Ancient terrain remains exposed because nothing replaces it. Dust moves, but it does not transform rock into soil capable of renewal. Ice shifts subtly, but it does not return as rain. Craters accumulate rather than fade. Time advances, yet the scenery remains familiar across immense spans. Renewal cycles define living planets. They do not prevent loss, but they offset it. On Mars, those cycles have ended. What is removed stays removed. What cools stays cool. What thins does not thicken again. The planet no longer adjusts when conditions drift. It absorbs change and settles. This absence of recovery shapes everything. Without renewal, there is no second chance built into the system. Mars cannot respond dynamically to variation. Solar radiation increases gradually as the sun ages. Mars will not compensate. Its thin air will not adapt. Its ice will respond passively, sublimating or retreating further underground. The planet accepts influence rather than shaping it. The silence that accompanies this state is not absolute. Wind still passes over the surface. Dust storms still rise and fall. Ice still cracks faintly under temperature shifts. These sounds, if they could be heard, would be sparse and isolated. They do not signal ongoing transformation. They mark repetition within fixed boundaries. Mars is lonely because nothing answers when something fades. No system steps in. No feedback restores balance. The planet's components coexist without conversation. Interior, surface, and atmosphere share space but not function. Each persists independently, governed by inertia rather than interaction. This loneliness extends beyond Mars itself. In the solar system, it is the closest example of a world that nearly sustained life and then did not. Its silence echoes because it once held activity familiar to us. Valleys suggest flow. Minerals suggest chemistry. The absence of renewal highlights what those features can no longer do. Mars orbits in silence, not because it lacks motion, but because its story has stabilized. There are no new chapters forming, only the preservation of old ones. Time continues, yet change slows to a whisper. The planet does not anticipate a future different from its present. No recovery does not mean collapse, it means resolution. Mars reached a state where further evolution became constrained rather than creative. The planet did not break, it finished transitioning. This is the loneliness of a failed world, not one destroyed or erased, but one that arrived at an ending without drama. Mars continues faithfully along its path, carrying the memory of cycles that once linked its systems together. Now those links are gone, leaving a world intact, silent, and alone with the shape of what it became. Value does not depend on vitality. Mars offers this truth quietly, through what it still carries rather than what it lost. The planet no longer supports life, yet it continues to give generously, not through abundance, but through preservation. What remains on its surface and beneath it has become a gift that grows richer with time. Mars gives knowledge by holding still. Because it stopped renewing itself early, its landscapes were never erased by constant recycling. Ancient surfaces remained exposed. Layers were left stacked rather than folded or subducted. Chemical traces stayed where they formed. This stillness allows scientists to read sequences that would be unreadable elsewhere. The planet retains evidence in plain view, waiting rather than hiding. In its rocks are records of water chemistry, atmospheric composition, and surface conditions from a time when many worlds were changing rapidly. Minerals formed only in specific environments remain intact. Sediments settle where lakes once stood. Patterns of erosion reveal flow directions and durations. Each detail carries information about processes that shaped early planets, including Earth, but vanished from Earth long ago. Perspective emerges naturally from this clarity. Mars shows how worlds evolve when systems fall out of balance and are not restored. It provides a reference point, not as a comparison meant to alarm, but as a context that sharpens understanding. By observing Mars, scientists see that planetary habitability is not a default state. It is a condition maintained through interaction, timing, and persistence. Earth often feels permanent because its changes are masked by renewal. Continents move, but coastlines remain familiar. Oceans recycle crust, but the surface appears stable. Mars strips away that illusion. It shows what happens when renewal ends. The contrast reframes Earth not as inevitable, but as contingent. Survival becomes something that must be sustained rather than assumed. Mars also offers a record Earth erased. On our planet, plate tectonics consumed early surfaces. Erosion softened features beyond recognition. Water reshaped landscapes repeatedly. Traces of Earth's first billion years survive only in fragments, scattered and transformed. Mars preserves a clearer version of that lost era, frozen in place rather than rewritten. By studying Mars, scientists reconstruct stages of planetary history that Earth no longer displays. They observe how atmospheres interact with surfaces under different conditions. They see how water behaves as pressure declines. They track the slow separation of systems that once reinforced one another. Mars acts as a companion archive, holding pages missing from Earth's own story. This knowledge extends beyond our solar system. Exoplanets are discovered in enormous numbers, many of them rocky and roughly Earth-sized. Without direct access, scientists rely on models informed by examples close to home. Mars anchors those models. It demonstrates one possible outcome among many. It shows how small differences in size, heat, and timing lead to lasting divergence. Mars gives perspective. By removing urgency, its lessons unfold slowly. They encourage patience rather than fear. The planet does not warn, it informs. Its history suggests that planetary futures are shaped over deep time, often without drama, through processes that appear ordinary while they are occurring. Even in its lifelessness, Mars continues to contribute. It supports exploration without deception. It offers data without distortion. Its silence clarifies rather than obscures. The planet remains honest because it no longer changes its answer. What Mars still gives is not hope for revival, but understanding. It provides knowledge of how planets work, perspective on how rare, sustained habitability may be, and a record of early conditions Earth can no longer show. In its quiet preservation, Mars continues to teach, not by becoming something new, but by remaining exactly what it is. Stories usually conclude with resolution. Mars offers something different. Its narrative did not arrive at a final chapter. Instead, it slowed until the next page never turned. What remains is not an ending, but a pause that never lifted. Mars did not collapse into an activity all at once. It continued forward long after its capacity for renewal faded. Rivers stopped returning, yet valleys stayed open. Atmospheres thinned, yet skies remained. Heat escaped, yet internal structures held their shape. The planet moved through change until change itself lost momentum. Progress gave way to persistence. This stall defines Mars more precisely than failure. A failed world implies interruption. Mars experienced continuation without development. Processes carried on within limits that never widened again. Wind moved dust without creating soil. Ice shifted without becoming water. Light warmed surfaces without altering climate. Each action repeated rather than advanced. In this state, time behaves differently. On an active planet, time produces layers of novelty. On Mars, time preserves rather than transforms. Features remain exposed not because they are young, but because nothing replaced them. Landscapes endure unchanged through spans that would erase entire continents elsewhere. The planet holds moments in place. This frozen narrative preserves potential rather than fulfillment. The conditions that might have led somewhere persisted briefly, then faded, leaving behind their outlines. Mars shows the beginning of rivers without their continuation. It shows chemistry without cycles to sustain it. It shows a surface ready for interaction, then left waiting. The pause is not accidental. It emerged from balance, settling into constraint. Systems weakened in sequence until interaction narrowed. Once that narrowing completed, the planet could not resume development. There was no mechanism left to restart growth. Mars did not stop existing. It stopped unfolding. This pause extends across every scale. Internally, heat remains insufficient to reorganize structure. Externally, sunlight arrives without consequence. Atmospherically, gases circulate without thickening. Surface features remain legible but inactive. The planet breathes shallowly, enough to persist, never enough to change its condition. Mars appears complete from afar, yet incomplete when read closely. The pieces of a living world remain present but disconnected. Water exists without flow. Energy exists without synthesis. Motion exists without direction. Each component holds steady, unable to link back into a system that evolves. This stalled story carries weight because it never resolved its tension. The question of what Mars might have become remains unanswered, not because it was forgotten, but because it was never concluded. The planet retained just enough capability to preserve its past, but not enough to shape a future beyond repetition. The pause does not degrade the narrative, it defines it. Mars stands as a chapter held open indefinitely. its last development suspended rather than finished. Nothing erased what came before. Nothing added what came after. The story remains legible exactly where it stopped. In that stillness, Mars becomes timeless, not ageless, but stable. It does not rush toward decay or renewal. It remains. This constancy makes it readable. Every detail marks a moment preserved instead of replaced. Each layer is a sentence left intact. Mars did not reach an ending because endings require closure. It did not stall because of sudden loss. It stalled because change narrowed until only maintenance remained. A story paused forever is not silent. It speaks through what did not happen. The planet continues to orbit, seasons cycling predictably, surfaces unchanged. Its narrative holds, suspended between what once worked and what never arrived. Mars exists as a story frozen mid-sentence, complete in its pause, enduring in the space where continuation once waited. Nothing about Mars ended suddenly. The planet did not collapse into ruin or fade overnight. Its transformation unfolded with patience, guided by physical laws that never rushed. Change arrived in small increments, each one reasonable on its own, each one narrowing what could follow. Mars changed slowly because planets do not hurry. Heat escaped gradually, air thinned molecule by molecule, water withdrew basin by basin. Each shift fit naturally within the one before it. No single moment announced a conclusion. There was no final season, no last storm, no single loss that could be named as the cause. The planet continued, altered but intact, adjusting to conditions it could no longer reverse. This predictability is what makes Mars legible. Its history does not contradict itself. The surface records align with the sequence of internal change. What scientists read in minerals, landscapes, and isotopes fits together without strain. Mars followed the path available to it, constrained by size, energy, and timing. Once that path narrowed beyond recovery, the outcome became permanent. Permanence does not require stillness. Mars remains active within its limits. Dust shifts, ice migrates subtly, temperatures cycle with the seasons. Yet these movements no longer build toward something else. They repeat rather than accumulate. The planet has reached a stable arrangement that persists not because it is ideal, but because it is self-consistent. The surface holds memory with unusual clarity. Ancient river channels remain visible. Sediments lie where water once settled. Minerals retain the chemistry of long-vanished environments. These features do not merely mark the past, they carry it forward, unchanged. Mars remembers because it stopped erasing itself. That memory transforms the planet into more than a destination. It becomes a reference. By observing what remains, scientists reconstruct what once existed. They trace how habitability emerged, lingered, and then retreated. Mars preserves the intermediate stages Earth lost to renewal. In doing so, it completes a broader planetary story. Mars did not fail because it lacked potential. It nearly sustained habitability for longer. It came close enough to leave a record, yet not close enough to maintain the systems required for endurance. Small margins decided its fate. Once crossed, they did not reopen. The planet's quiet evolution offers context rather than warning. It shows how worlds respond when key processes weaken without interruption. It demonstrates that survival depends on timing and reinforcement, not on any single feature. Mars teaches through consistency, not catastrophe. What remains today is not a dead planet in the dramatic sense. It is a resolved one. Its systems have finished transitioning. Its options are few, but reliable. The planet continues to orbit, unchanged in its essentials, carrying the imprint of everything it once was capable of becoming. In that endurance lies meaning. Mars stands as a reminder that stories do not always conclude with closure. Some pause indefinitely, held in balance by what can no longer change. The planet's surface continues to speak quietly, offering evidence without embellishment, memory without distortion. Mars did not die in a moment. It became something else through gradual, predictable change. Its surface still remembers what it once was, when water moved freely and air pressed down with weight. Those memories remain etched in stone and ice. And in that memory, the story remains,